All right, but actually, I just remembered one thing. If you have not yet done the course eval, another reminder to do that for bonus points. Okay, for bonus points, send me proof that you did it. All right, for 5 bonus points on exam 4. Another announcement I want to go ahead and make is, in case the end of class today feels rushed, while I have all your attention, I have so enjoyed having all of you in my course. I hope that chemistry has been made somewhat enjoyable this semester. I hope that more than anything, you've learned something. I hope that you've proven to yourself you can do hard things, because this has been a hard course and it's taken a lot of time and effort. And I value all the time and energy that you guys have put into this and the hours that nobody else has seen. So thank you for that. I wish you all the best moving forward. I just say that because I don't know who all, will be joining reviews next week. And I don't know if I'll see you guys again. So last other thing. There is going to be it's a 20-minute video on functional groups. Okay, functional groups will be 10 points of the exam, and that is already posted to Blackboard. Okay, 20 minutes, functional groups. Again, you'll have your notes for that. So typically I would ask people to memorize there's like 11 different functional groups, and I'll point the 11 out that I want you to know. There's a whole bunch, but just 11 that I want you to focus on. So it's no added memorization. Just have those notes and those tables. You'll see what I'm talking about when you watch the video on the functional group slides, which are already on Blackboard. Just have those available, printed out or whatever when you take exam 4, because you'll have to identify certain functional groups like on a molecule. Okay, and I walk through examples of that, and I'll do some practice problems on that as well Monday. Okay, pH, here we go. So we have been talking about concentrations of H plus and OH minus, but sometimes their concentrations are very small, okay? Like we were dealing with numbers, remember, like this on Tuesday, 1 times 10 to the minus 7, 1 times 10 to the minus 8. And sometimes those numbers are hard for our brains to like comprehend, like which one's bigger and which one's smaller. So because of that, we use the pH scale, and it's a scale from 1 to 14, and it's nice whole numbers. There are decimals between that, but it's easier to look at numbers between 1 and 14 and judge something versus numbers like 1 times 10 to the minus 7. All right, so that's kind of the use of the pH scale. So what is pH? All right, so P is a function. It's a mathematical function. All right, and you guys have probably heard of log before. You probably can look at your calculator and see the log button. You should have heard of log before. So it's a function that indicates log, that a logarithm is being used. All right, and specifically negative log. All right, so we can take P of anything. We can apply that function to anything. All right, and here we're applying it to the concentration of H plus in a solution, hydrogen ions. We're trying to judge the concentration of H plus, all right? So pH is the negative log of the concentration of H plus. That is how we calculate pH, right? Guess what? We could also calculate the concentration of OH minus. We call that POH. So it would be the same thing, negative log. You just do negative, punch the log button on your calculator, and whatever the concentration of OH minus is, you would plug in that number in the parentheses. We can take the P of a Ka value. pKa is what we call it. We'll run into that a little bit. Any number, we can take the negative log of it, all right? And that's what P stands for. All right, so if I tell you pKa later, just know that is if I have some K, remember that table of Ka values for weak acids? Okay, you could take the negative log of any of those values, and that's pK, all right? You could get POH and pH as well. We're going to focus on pH, but here's what you need to know. Because I said pH scale is from up to 14, we have an equation. It's a very simple equation. Actually, sorry, hold on. pH plus POH, okay? When you take pH, if you were to calculate POH as well, and you add those together, the sum will be 14. All right, so keep that equation just kind of in your back pocket. It's a very simple one, and we'll use that as well in a little while. You're going to find there's different ways to solve for things with this equation or equation for KW. And whichever one you think is most simple or makes most sense to you, I'll tell you to use. Okay, so let's actually calculate pH. Are the following concentrations, first off, here's a question. Are the following concentrations less, would we consider neutral? Okay, so how do we judge that? Let me scroll up because I'm going to remind you what we looked at on Tuesday. There's our end of semester meme. There's our horse friend. Right here, okay? Remember how we classify things as acidic, basic, or neutral are based on the levels of the concentration of H plus. So if H plus is greater than 1 times 10 to the minus 7, that's acidic. If it's equal to, it's neutral. If it's less than, it's basic. All right, so let's go back down and now we can judge those things. So 1 times 10 to the minus 7, is this acidic, basic, or neutral? What do you guys think? That's what we said was, okay, thank you, Lucas, neutral. All right, so what is the pH? So grab your calculator. You need to do the negative log of this number. So we're going to do pH equals the negative log of 1 times 10 to the minus 7. What do you get? If this is neutral, what would you imagine the pH is? Anybody get it yet? 7 point something. I got 6. Negative log of 1 times 10 to the minus 7. You should get 7. You should get exactly 7. Okay, so pH here, double check, should be exactly 7. Okay, thank you, Rachel. All right, that's okay, great. Okay, so that's neutral, pH is 7. Let's do the next one, 1 times 10 to the minus 9. So just delete the exponent, re-enter that same equation, delete the exponent, change it to a negative 9 instead of a negative 7. And then we also have to classify, is this acidic, basic, or neutral? 1 times 10 to the minus 9, is this bigger or smaller than 1 times 10 to the minus 7? I know the exponent there is 9 is bigger than 7, but remember we're on the negative scale. So 10 to the minus 9 is smaller. So we would consider this basic. And Will said it's, when you do pH of negative log of 1 times 10 to the minus 9, we get a pH equal to 9. Someone go ahead and do the last one. 1 times 10 to the minus 4. Is this acidic, basic, or neutral? What do you guys think? 10 to the minus 4.
Acidic.
Yes. Well, not AS.
4.
ACID. Okay, and we got a pH equal to 4. Do you guys notice a trend at all?
Yeah, it's the same as the exponent.
Okay.
Positive.
When, let me erase over here. When your base unit or number is 1, okay, and not 2.3 or 3.5 or some random number, when it's 1, yes, pH is equal to the exponent. That's what you see right down here. So if the concentration of H plus is a 1 times 10 to some negative exponent, pH is equal to that exponent, okay? But you cannot always assume that because your base number isn't always 1. And if it's not 1, how would you calculate it? You just plug it into the calculator, okay? So again, these are giving you your guidelines for acidity, basicity, and neutral solutions, okay? pHs that are less than 7, those are acidic pHs. So down from 7 towards 1, it is more and more and more acidic. So a pH of 1 is very, very acidic and corrosive. A pH of 6 is acidic, classified as acidic, but kind of a neutral acidic. Not going to be as harmful, all right? And then anything above a 7 is considered basic. And then here's a figure from your textbook listing a whole bunch of different items and their acidity, okay, to kind of give you some ideas of things that we come into contact with, you know, fairly regularly, and what their acidity is. It also gives you the concentration. It says H3O plus, which we know is just the concentration of H plus. So the pH and the corresponding concentration of H plus. So I guarantee you there's going to be times on the exam where I say, here's your concentration of H plus. What is the pH? All right. So you can come to this exact figure and judge based on like what your exponent is, what the pH should be around. You can always use this kind of double check. Am I close? You know, but always plug it in your calculator to determine it exactly. Okay. All right. Questions on these figures? One other thing I want to point out, as the concentration of H plus increases, so this is the smallest concentration, 10 to the minus 14. As you go down, it increases, okay? All the way to 10 to the minus 1 would be the biggest. So as H plus concentration increases, look what happens to OH minus concentration. It decreases. Okay, they're like inversely related. As one increases, the other decreases. Why? Because we know these concentrations always equal a constant when they're multiplied, Kw. So as one decreases, the other has to increase, and vice versa. All right. I've actually already talked about this slide. What if the concentration is not a 1 times 10 to the minus something? Like what if it's 2? And then you just put in your calculator. All right. And you actually calculate it. So the example would be here, what is 2.3 times 10 to the minus 6? Okay. So this is between 1 times 10 to the minus 5 and 1 times 10 to the minus 6. So this number is in between that. Okay, so it should be in between a pH of 5 and a pH of 6. We just don't know exactly. We just have to calculate it. Anybody calculate it for us?
5.64.
5.64. Okay, you just do the negative log of that value. Okay, questions? So you can always kind of judge it and know what it should be close to, but have to calculate its exact value. All right, so that's how to calculate pH. But now I want to look at an actual solution. Say we have HCl. Okay, what kind of acid is this? Strong or weak? You can always look at that table. I would have that table handy. What table am I talking about? The one 10.1, acid base strength. It had the blue and the red arrows on it. That's going to be on your resources page. But you definitely need to have that. So have that handy. Kylie says strong. That's right. Okay, so it's going to completely disassociate. Let's draw that out. HCl disassociates to H plus and Cl minus. So to calculate pH, we need the concentration of this guy, H plus. Now, initially, we say we have a solution of 1 times 10 to the minus 6 of that, and we have 0 of these things. But we know that it's going to 100% disassociate in solution. So we're actually going to end up with 0 of this and 1 times 10 to the, we're going to get all products. So how would we calculate pH? Knowing this is a strong acid, that was the first thing. We know that it completely dissociates. How would we get pH? Well, we now know the concentration of H plus, right? So we just take the negative log of this number, and that equals pH. Okay, so here there's just an added step. I give you an acid in a solution, and then I'm asking you what pH is versus just giving you a number and saying what is pH. Okay, so here we just had to understand and determine our concentration of H plus with one additional step, and then we can calculate pH the same way. How did I know it was strong again? Bailey, you can look directly at that table. I would love to hold on, actually I will. That table, oh no, it's down. Sorry, I'm scrolling just a little bit. Right here, this table right here, Bailey. Okay, you can always look at this table and say, oh, I see that it's a strong acid because HCl is right here. Does that make sense? I'm not going to ask you about anything that's not on this table. And if I do, then I will tell you, hey, this is weak, or hey, this is strong. Nope, wrong lecture. Wrong one. Okay, here it is. All right. Okay. Oh, by the way, is this acidic, basic, or neutral? So what is our pH? Anybody get it?
6.
Okay, so our pH is equal to 6 when you do the negative log of that, or you could just look at the exponent since it's 1 times 10 to the negative 6. Is this acidic, basic, or neutral? Based on the pH scale that we just saw on that figure right up here, okay, pH 6 is slightly acidic. Okay, what about this? We have same acid, so we know it's a strong acid. So again, when you're given a strong acid, you can automatically say this, whatever my concentration of the acid is, that equals my concentration of H plus. So I'm just gonna go ahead and write that out. The concentration of H plus is gonna be equal to 4.5 times 10 to the minus 4. because we know H plus, just like what we wrote right here, is going to completely dissociate.
Okay, Beverly.
Yes, Blake?
When we're determining if it's neutral, acidic, or basic, are we going off where you said the pH equals 6, or are we going off the 1 times 10 to the negative 6?
Right here, pH equals 6. So the pH scale, 14 is the most basic, 7 is neutral, and 1, or, you know, even anything a decimal less than 1 would be very acidic. Okay, so anything from between 6 and 1, that's acidic. And a pH of 7 is neutral. Anything, you know, 8 to 14. Now, if you have a pH of like 7.5, I would still consider that neutral.
Okay.
Great question, Blake. Okay, so here's our H plus concentration. Did anybody calculate it yet? So we need it. How do we get pH?
Negative
Equals the
log.
negative log of 4.5 times 10 to the minus 4. All right, so we don't have a nice base number of 1 here. So pH is going to be around 4 because our exponent is a negative 4. But we need to actually put that in a calculator. Anybody have that?
3.35.
So do we consider this acidic, basic, or neutral? It's between 1 and 6, right? So it's
Acidic.
actually pretty acidic. Okay. So you guys feel okay if I give you any sort of acidic solution, I tell you the concentration. Now, if it's a weak acid, it's a whole different ballgame. Okay, we are just doing stuff with strong acids right now because we know the concentration of H plus equals the concentration of our strong acid. All right, different ballgame when you have weak acids, and we'll actually solve one of those in a little bit. Okay, what is the pH if we have 1 times 10 to the minus 3 molar KOH? So this is not an acid, this is a what? KOH. You should immediately recognize this as a base. So it was a solution with a base, and we're asking what's the pH? How do we determine that? What can we do? Anybody remember the equation I wrote earlier? Could we get POH? Okay, so knowing that this is a very strong base. Yeah, we can do the negative log of OH to get POH. But what is the concentration of OH minus? Just the same way we did with strong acids here, because it's a strong base, we know KOH in solution will completely disassociate to K plus and OH minus. Completely. Remember, that's the nature of strong things. So the concentration of OH minus will be equal to our concentration of base here. So it's going to be 1 times 10 to the minus 3 molar. So P of OH is what Grant typed in the chat there. We can just do the negative log of 1 times 10 to the minus 3, but we have a nice base number of 1 here. So guess what our POH is?
3.
3. So how do we solve for pH now?
You just subtract it, the POH.
Yep. So pH now equals 14 minus 3. We're just subtracting POH from both sides of the equation. pH equals 14 minus POH, and our POH is 3 here. So pH equals 11. Okay, one other way, if you're like, oh gosh, I don't know, I don't like this. You know, when you know the concentration of one ion, you can always find the concentration of the other using Kw, because Kw equals H plus times the concentration of OH minus. Remember that? So this is the concentration of OH minus, and we know Kw is 1 times 10 to the minus 14. So you could say 1 times 10 to the minus 14. And then we would want to divide both sides by OH, right? So we would divide it by 1 times 10 to the minus 3, which is our concentration of OH minus. We could get the concentration of H plus that way. And we can always take the negative log of that to get pH. Okay, but if that's like, again, sometimes people just like this equation a whole lot better than doing all the 10 to the minus 14 stuff. But there's 2 ways you could solve for that. Okay. So you calculate this value, 1 times 10 to the minus 14 divided by 1 times 10 to the minus 3, which should be 1 times 10 to the minus 11. And then you would take the negative log of that to get pH, which is how we got 11. All right, so 2 ways, but again, if you like the POH and pH equals 14, just stick with that. Questions so far? All right, now there's one other thing I want to teach with pH scale, and then we're going to move on to buffers. So the one other thing I want to teach is if you are given the pH, like I say, your pH is 5 or 5.5 or 3.2, and I want to know what the concentration of H plus is. Sometimes when you're examining things within the body, levels of H plus need to be calculated, okay, from a pH. So how do we do that? Well, by the way, there's this link here. You can just copy and paste that right off the slide if you download it. And it's a video that walks you through this as well, step by step, if you want to rewatch what we're about to do, okay? So we know this equation, pH equals negative log of H plus. So how do we solve for H plus? We've got to undo a couple of things, okay? We've got to isolate H plus. So first off, move the minus sign over. When you do that, you get negative pH equals log of H plus. Okay, so just like you're dividing both sides by a minus. All right, then you take something called the antilog. Anybody ever heard of an antilog? How you undo a log function? Okay, logarithmic functions have a base power of 10. Okay, base power of 10. So what that means is we're gonna essentially raise both sides to an exponent with a base of 10. So what that looks like is 10 to the negative. We're gonna raise whatever we have to the exponent portion with a base of 10 equals 10 to the log of the concentration of H plus. And what that does is it undoes the log. It takes the log away. So we no longer have an exponent here. We just have 10 to the negative pH. That equals the concentration of H plus. So what if I give you a pH, like your pH is 6, in your calculator, you'll type in 10 to the power of negative 6, okay, negative pH, that equals your concentration of H plus. All right, I'm not going to ask you to derive this equation. You just need to know this off of this slide. So let's put this into practice. So you have a pH of solution, you have a solution has a pH of 8. What is the concentration of H plus? So again, looking at this equation, our pH is 8, so we'll say 10 to the negative 8. And so that equals what? 1 times 10 to the negative 8 molar. That's going to equal our concentration of H plus. It's easy when you have whole numbers as your pH. It's not as easy when you have decimals. You have to put that here. You didn't necessarily have to put this in your calculator. But now look at the very next one. Now we have 4.5. Same thing here. You're just going to do 10 to the negative 4.5. Now here, when you punch this into your calculator and you hit enter, it's going to give you a different value. What value does it give you? Because we don't like decimals in our exponents. You can't keep a decimal in your exponent. You have to put this in your calculator, hit enter, and it's going to give you a different value. What do you get? $10 to the negative 4.5. We get it? Okay, Bradley said 3.16 times 10 to the negative 5. Okay. See how your exponent is a whole number when you finish? Your exponent always needs to be a whole number, not a decimal. Okay. All right, and that's units of molarity because we're expressing a concentration. Okay, we always indicate concentration with the brackets, right? So the bracket of H plus, it means concentration of H plus. And your exponent needs to be a whole number. Okay, what if pH is 12.3? Now I'm asking you what is the concentration of OH. So notice I'm giving you pH and I'm asking you for OH. So we have an extra step we need to do here. What could we do? We need to get POH. We don't want pH, we want POH. How do we get POH? Remember, 14 equals pH plus POH.
So what
So
we
first let's
subtract?
subtract pH. So I'm just gonna erase and plug in my 12.3 there. So minus 12.3 from both sides. So 14 minus 12.3 is 1.7. And that equals POH. Now, same thing as we did with pH. If we know pH, same idea. If we know POH, we just do 10 to the negative 1.7 equals the concentration, this time not of H plus, but of OH minus. So we just had to do one additional step here, get POH, then you do 10 to the negative of that, get concentration of OH minus. When I put that in my calculator, I get 0.019, well, actually, basically 0.020 when you round, molar, okay? Or you could say 2 times 10 to the minus 2. Okay, so for sure on the exam, maybe with multiple choice questions, probably is how I usually do it. I'll give you a solution. I'll say, what's the pH? I might give you the pH and I say, what's the POH or what's the concentration of OH minus? All right. So any questions on what we've gone over so far? If you're like, I think I get the hang of it, but I'm not totally sure, you need to practice, right? So go through today on the homework and find the homework questions that have you practice this. Again, I'm not asking you to do the whole homework today. Just do 5 or 6 problems to kind of reinforce this concept, all right? Get the hang of it. I'm going to skip over this whole slide. We just don't have time for today. It's really about the logarithmic scale. I'm not going to ask you any questions about this on the exam. Well, here's what I really want to get to. Solving pH, what if we have a weak acid? So far we've looked at strong acid and strong base, and how do we calculate things like pH and POH? What if we have a weak acid? Okay, you have to use the equation for Ka. There's just no way around it. So the first thing I'm going to do is write step 1, what is the dissociation reaction or equation? Dissociation equation or reaction. I'm just going to write, we have carbonic acid here. What happens when that gives away hydrogen? I'm just going to write that equation. And you should get H2CO3. We have a weak acid, so we have a double arrow. Makes HCO3 minus. We're just looking at giving away one hydrogen. And H plus. Okay, that's the dissociation reaction. So now we write Ka for this, which is products over reactants. Okay, it's just all coefficients of 1 here. So Ka equals concentration products, which is H, this is bicarb, times the concentration of H plus over the concentration of our reactant, H2CO3. Okay, remember it's products multiplied by each other over reactants. Okay, which portion of this equation can we get pH from? Which portion are we really interested in? Well, what is pH? pH equals negative log of H plus. So there's one piece of this whole equation that we really want to know. That's the concentration of H plus, right? Okay. This isn't in the slides? Was this a problem that I added okay, I'm sorry. Take a screenshot of the problem. I'm very sorry. I thought this was in your slides. Thanks for letting me know. All right. I'm gonna go find. We need a couple things. We need to know what the Ka of this acid is. We know it says. I haven't even read the full problem, have I? Carbonic acid is part of our blood buffer system. What is the pH of a solution where the concentration of H2CO3 is 1.7 times 10 to the minus 3? So we know Ka. We can get that from a table that I'm going to show you in a second. And we know the concentration of H2CO3. So we know those two pieces. Okay. Here's what we also know. We also know that every time one molecule or one H2CO3 dissociates, that we'll get one of these and one of these. We'll get one bicarb ion and we'll get one hydrogen ion. So no matter if 100 molecules of carbonic acid or 1,000 or 1,000,000 molecules of carbonic acid dissociate, we know that we're going to have equal numbers of these ions. Okay. Equal numbers. So what that means is the concentration of your products will be the same. Okay. So remember what I did the other day? We plug in X. Remember when we plugged in X for Kw when we're trying to solve the concentration of hydrogen and hydronium ions? Or sorry, hydroxide and hydronium? We're going to plug in X on the top here. Okay, so what this equation becomes is Ka equals X times X, because we're just going to say the concentrations, whatever they are, they're going to be the same. So we're just going to plug in a variable of X for both of those things. This is Ka over the concentration of H2CO3, which we know that value, and we'll plug in the numbers. So how could we rearrange this equation? What is X times X?
X squared.
So I'm actually going to erase and write that in. So we're going to say this is our new equation. So this is key for weak acids. It's key that you understand the concentration of your products here. The two ions are going to be identical. So if we solve for X, guess what? We solve for the concentration of H+, and then we can get pH. So let's go find Ka. I think it's right here. Ka for carbonic acid is 4.3 times 10 to the minus 7. So this is Ka, right? This is a table of Ka values. So we need this value, 4.3 times 10 to the minus 7. That is Ka. So I'm going to say 4.3 times 10 to the minus 7 is going to be equal to X squared divided by our initial concentration of the acid is 1.7 times 10 to the minus 3 molar. That was initial concentration of H2CO3. All right, you guys tell me what to do. I think y'all can take it from here.
Multiply both sides by the 1.7 times 10 to the negative 3 molar.
That's right. So what happens? It cancels on this side. It goes away. If it cancels and goes away, I'm just going to erase it. That's after I've cross multiplied. So now I have 1.7 times 10 to the minus 3 times our Ka value equals X squared. And then lastly, you just take the square root of both sides, right? So I'm going to do the square root where is my square? Oh, there it is. Of 1 times, 1.7 times 10 to the negative 3 times, somebody's going to beat me on the answer, times 4.3. I'm not competitive. Times 10 to the negative 7. Okay, what did y'all get? I got 0 point, let's see, 1, 2, 3, 4. Well, I'm actually going to write it as scientific notation. I knew it, Brooklyn. 2.7 times 10 to the minus 5. That's what I got. Molar. That equals x. That equals x. Okay, because we took the square root of x squared. So that equals x. And remember, we just plugged in x for these things. That's what we plugged x in for. So when you solve for x, you just solved for the concentration of H+. All right, this is one of the hardest style problems I think we're going to do in chapter 10, besides a buffer problem. I think buffer's hard too. Okay, so now to get the pH, what do? What is pH? Well, here's our equation for pH. We take the negative log of that. So I'm going to do negative log of that value. So negative log of 2.7 times 10 to the minus 5 equals concentration of H+, or sorry, that equals pH. And I got 4 point, we round, it's 4.57. So I'm going to go back in and write our steps. The first step, I started to write our steps and I lost track of that. Step 1, we wrote the dissociation reaction. Step 2, we wrote the Ka expression. Step 3, we plugged in X for the top, for the products. Step 4, we rearranged our equation and took the square root of both sides. Rearrange and take the square root. And then step 5, this is a 5-step problem here. You take the negative log of your value for X, which is H+, and you get pH. Okay. Questions on, this is specifically, I cannot emphasize this enough, for weak acid. You don't do this for strong acids. We already solved pH for strong acids, very easy. Okay. It was a 1 step for strong acids. This is just for weak acids. Okay. Questions on what we did here? All right, we're on to buffers. That's pH. Okay, so what is a buffer? A buffer is a combination of substances in a solution that act together to resist changes in pH. Okay? It's a combination of substances in a solution and they act together to resist changes in pH. All right, so buffers want to maintain a certain pH. It's crucial to do this in biological systems in the lab. So in I think there should be an A there. Laboratory solutions. Yes, Rachel, from 9:30 to 10:30 it will be recorded. Right. So biological systems, there's certain laboratory solutions we got to have a constant pH. And here's the main thing though. A buffer is usually a weak acid and its conjugate base. A buffer is composed of a weak acid and its conjugate base. Those are the 2 components. This is a weak acid solution. So here's the general equation for an acid with water. Which one's the weak acid? Which one's the conjugate base? Can somebody tell me? Which one's the weak acid?
HA.
Which means the conjugate base is, once we give away the hydrogen, what's left over, this is the conjugate base. Right? So if you're looking at, this is acetic acid right down here. This is the acid in vinegar, which is what we're using in our vinegar titration lab this week. So the the weak acid is not water, it's the acetic acid, and acetate would be the conjugate base. Okay. Water is the base here, and H3O plus is the conjugate acid. Okay, so that's essentially what a buffer is. Now we're going to look at how do buffers work. Okay, so that's what a buffer is. It's a solution that has a weak acid and its conjugate base. How do buffers work? How do they resist changes in pH? Well, resisting a change in pH indicates that something is trying to change pH. Okay, so what can change pH? What could affect pH? What would an acid do to a pH? That's right. So acids generate H plus in solution. H plus lowers pH, okay? I'm gonna write this right up here actually. I'm gonna zoom in. The concentration of H plus affects pH. The more H plus you have in solution, the higher its concentration, the bigger, the lower pH goes, all right? What about OH minus? It's a base. The more of that you have, the higher pH goes. All right, so these are some trends to remember. The more H plus you have, the lower pH goes. The more OH minus you have, the higher pH goes. Okay, makes it more acidic or more basic. H plus makes it more acidic, OH minus makes it more basic. All right, so let's say we have at equilibrium a weak acid, HA, and it is in equilibrium with its conjugate base. Excuse me. All right, let's say you add some base. Like we're going to add a little bit of sodium hydroxide. Okay. You can ignore the sodium here. Okay, but we're adding a strong base. That could threaten our pH. It could threaten to raise our pH, and the buffer doesn't want that to happen. So buffers have components that can neutralize what's being added. All right. So what do you think is going to neutralize OH minus? An acid or the conjugate base component? Do you think acids neutralize bases, or would a conjugate base component neutralize a base? Yeah, acids. So this weak acid here sees that OH minus floating around in solution, and it's like, nah, I'm gonna neutralize you. So they essentially react together. Okay. And what does the acid do? The acid's going to donate its hydrogen to OH minus. What are you going to make when you do that?
Water.
Can water change your pH? Can water affect pH? No, water's not a threat to pH. It's neutral. Okay, so that's how we neutralize the base. Any base that's added to this buffer system, that weak acid is on it. Okay, so remember this. Acids neutralize bases. Okay, so it's the weak acid component here that's going to go into action and neutralize any base that we add. And then in the process of that, we generate more of our conjugate base. All right. So what happens when you add some base? I'm going to make a point over here. Point number 1, when base is added, the concentration of HA goes down. Okay, why? Because it's being used up. It's being used up to neutralize the base. And the concentration of A minus inherently goes up by a little bit. Because one thing's being used up and one thing is being generated in the process of neutralizing the base. Okay, what about if we add some acid, like a strong acid, like HCl? That can threaten our pH. It can threaten to lower our pH because we know it's going to create a whole lot of H+. HCl will dissociate and make a whole lot of essentially H+. That's the guy that could threaten pH once it dissociates. So which portion of the buffer here can neutralize an acid? Do you think the weak acid can neutralize an acid, or the conjugate base could neutralize the acid?
The base.
So this conjugate base sees that H+, the A minus here. And remember, A minus is just standing for, there's so many different buffer solutions. So we're gonna, when we actually put this into play with a real buffer, we would plug in our actual formula for a conjugate base. But here we're using A minus to represent any general conjugate base, all right? So it sees that H+, and they're gonna react, they're gonna collide. And what is that gonna make? A minus and H+ makes what? Look what it makes. Okay, it makes weak acid. Weak acids do not affect pH very much at all. Strong acids do. Weak acids don't dissociate a whole lot, okay? So they don't affect pH very much. Okay, so here the point to make is that conjugate base neutralizes strong acids. That's what you see here. So point number 2, and I actually might move that right down here, because point number 2 is that when acid is added to the buffer, the concentration of A minus goes down. Concentration of HA goes up because we're going to make more of it. Sorry, I'm just seeing. I do not have office hours on Friday because I'm going to be in lab all day. I normally do, but I'm going to be in lab with students. Okay, so if you need to meet with me or talk about any of this, email me and we can set up a time outside of those office hours. Okay, if you are lost on this stuff, we're about to work some example problems and maybe that will help. Okay, but this is a diagram. This is a buffer diagram to show you how how buffers work, how they neutralize anything that is added to a buffer solution. Okay, so right now you could imagine this in a beaker or a flask on a lab bench, but this is going on in our bodies. Okay, it's a very dynamic situation. Right, this is what our blood buffer system does. This is what buffers in our cells do to keep the pH of our cells constant. All right, so it's not just happening in beakers on lab benches. It's happening in your blood and all throughout your bodies. Okay, so here's that same diagram, all right? This is indicating any base that's added to the buffer. This is indicating any strong acid that's added to the buffer, all right? And these are our buffer components that are in equilibrium, HA, the weak acid, A minus, the conjugate base. Okay, so let's imagine we have a real buffer system with acetic acid and the acetate ion. What would happen to pH if we added NaOH, a strong base? But we're not adding it to the buffer yet. It says, what would happen if we added NaOH to water? Think about that. What does NaOH do? We said up here, the more OH you have in a solution, the higher pH would go. So if we're adding NaOH to just some water, water's not a buffer. It has no ability to neutralize anything. Okay, so it would raise pH. Okay, we have no buffer in place. So inherently, pH would go up. But now, if we have the above reaction, so this is a buffer. We have a weak acid and a conjugate base. So essentially, we're saying what happens to to pH if we add NaOH to a buffer? We'll look at our diagram. The OH minus and the weak acid component, so the CH3 COOH, they'll react. So we'll get this reaction right here, CH3 COOH plus NaOH. These are the two that are going to eye each other out and they react. So this will donate, this will accept, and we're going to make water. Okay. And we'll get a salt. We'll get sodium acetate. But look, we've neutralized our base. So what happens to pH? That's the ultimate question. What would happen to pH? What do y'all think? If we're making water, if we're neutralizing our NaOH, what's going to happen to pH? Nothing, right? It's not going to change. pH will not be affected. Okay? Because this is what a buffer does. It's resisting a change in pH by neutralizing anything we add to it. All right, what will happen to pH if we add HCl to the above reaction? This acetic acid reaction up here. What would happen? Remember the buffer diagram. We add HCl. Which component in here do you think would react with that HCl? Let's go back to our buffer diagram. Conjugate bases neutralize strong acids. So which portion is the conjugate base? This one is the weak acid. This one, acetate, is the conjugate base, right? So the conjugate base is going to go into action here and neutralize that HCl. So the reaction that will happen is CH3COO minus. This is the conjugate base. It'll see that HCl in solution, and the lone pairs here will grab up that hydrogen. It's just an acid-base reaction. And it will make CH3COOH. It makes more of your weak acid component. Remember, you make more of the weak acid. We said the concentration of the weak acid goes up. It makes more weak acid, so it's neutralizing. So the conjugate base will neutralize the HCl. So what's going to happen to pH? Will pH be affected? If we're neutralizing, HCl could drop pH a lot, but in a buffer it won't, because the buffer is going to neutralize it. Okay, so pH will not be affected. Okay, can y'all give me some emojis here? By the way, please turn your cameras on if you can join us. I'd love to see some faces. Can we give you some emojis, like a thumbs up or a thumbs down? How are y'all? Do you feel like, if you're grasping, like, I won't say 100%, but if you feel like you're grasping 50 to 75%, give me a thumbs up. If you're like, I'm just not, I'll be honest, give me a thumbs down. Like, I'm still quite lost. Okay. I was good until we hit buffers. Okay. All right. Here's what I'll say. Spend some time walking yourself through the buffer diagram. Redraw it if you have to. Okay. I'm wondering, I wish I had time to look and see if Khan Academy had like a good buffer video. Not because I want you to just like, not because I don't think I'm doing a good job explaining it. I know sometimes it can help when you hear it from somebody else too. All right, do know that this is recorded. If you are lost and you need to rewatch some of it, we've got 15 minutes left. So we've got to get to finding pH of buffers. So it looks like we're probably not going to get to buffers in biological systems today, which is like a really big bummer. I don't know what I'm going to do about that. I don't think I'm going to be able to do anything about it. But we've got to solve for pH of buffers. So we're going to solve a buffer problem in our last 15 minutes. Okay. So what does this mean? We are going to examine how do we find pH of buffers. Okay. So we've looked at how do we find pH of just regular solutions that maybe have a weak acid or a strong acid. Well, we said that buffers resist changes in pH. How do we actually find pH of buffers? Okay. It has everything to do with this equation here called the Henderson-Hasselbalch equation. All right. So basically, because we know buffers have a weak acid and they have a conjugate base, we can find the pH if we know the concentration of these things. This Henderson-Hasselbalch equation is derived from an equation of Ka. I'm going to spare you all deriving this. You just need to know this equation. You don't have to memorize it, obviously, because you'll have it on your notes. But what it says is that the pH, this is specifically for a buffer. So if I ask you what's the pH of a solution of HCl, that's not a buffer. That's just a strong acid. Do not use Henderson-Hasselbalch. You just use negative log of H+. If I ask you what's the pH of a buffer, you're going to say pH equals pKa. We introduced that term earlier. pK, that's the negative log of a Ka value, plus the log of the concentration of A-. Okay, that's our conjugate base on top, divided by the concentration of our weak acid on bottom. Okay, the log of those things. So pH equals pK plus the log of the concentrations of our conjugate base divided by the concentration of our weak acid. Okay, so there's our equation. We'll look at how it goes into effect. I'm going to jump over these. I just have to, sadly. So it's probably not going to be on the exam, but a buffer problem will be on the exam. Yeah, probably not this one either. We've got to get to a buffer problem. All right, so using Henderson-Hasselbalch equation, which is right here, that's the Henderson-Hasselbalch equation. We're going to learn how to calculate pH of a buffer. So what is the pH of a buffer solution that has 0.1 molar HF hydrofluoric acid? That's on your acid base table. And it has 0.12 molar NaF. All right, so this right here is the weak acid. This right here is the conjugate base. All right. It has that cation for sodium on there, but essentially we're just saying HF is the weak acid, F- is the conjugate base. How do you tell which is which? The one that has hydrogen in it, an acidic hydrogen, is the weak acid. Okay. The one that has the acidic hydrogen is the weak acid. Yeah. So like for acetic acid, if we did one with acetic acid, it would be CH3COOH would be the weak acid, CH3COO- would be the conjugate base because it's missing that acidic hydrogen. These, remember, hydrogens bonded to carbons are not acidic. It's the ones in the carboxylic acid group. All right, so we can calculate pH, right? We're given the Ka of our weak acid. By the way, if I tell you the Ka of HF, I'm telling you the K of what the weak acid is. So this as well tells you, oh, that one's the weak acid if you're still unsure. So let's get the pKa. So we need pK equals the negative log of Ka, which is 3.5 times 10 to the minus 4. Okay, I've got to plug in pKa to my equation to solve for pH, so that's why I'm trying to get the pKa. So what is that?
.46.
Awesome. So pKa equals 3.46. All right, so we've got this piece. And guess what? We already have these concentrations. They're given to us. So anytime you're just calculating pH of a buffer before anything is added, like a strong acid or a strong base, all you do is you calculate pKa and you plug everything into Henderson-Hasselbalch. So here's what that looks like. pH equals, now I'm going to plug in my pKa, right? Because it equals pKa 3.46 plus the log. I'm just literally following this equation step by step. pKa plus the log of which number do I put on top? Which one do I put on bottom? Yeah, I put my conjugate base on top. That's NaF. So 0.12 molar goes on top, 0.1 molar goes on bottom. All right, so literally you're just gonna do, this is not negative log, okay? So don't take the negative log of that. Pay attention to the equation. It's positive log, so I'm doing the log of 0.12 divided by 0.1, close your parentheses. When you do the log of those things, you get 0.079. So now pH equals 3.46. That was our pKa plus the log of those values. So the pH of our buffer overall is equal to 3.54. pH is unitless, right? No units here. That's kind of nice. Classic mistakes. People will plug in Ka instead of solving for pK. They'll forget to do that. Or they'll switch your concentrations and they'll put the wrong number on top and bottom when they do the log. Okay, I know some of you are probably still feeling lost on buffers. Please meet with me or please show up Monday. I'm going to work through these things again. Yeah, if I find videos online, absolutely, Bailey. Okay, let's keep moving. We got 10 minutes left. So that's a buffer, by the way, has three parts. Okay, a buffer problem. There will be one buffer problem on the exam. Step one is you just solve for the pH of the buffer, like we just did. Step two, part two, is you look at what happens when you add a base. Okay, what happens when we're adding base? How do you solve for the pH? How is it affected? Okay, so again, buffers are resisting changes in pH, but it doesn't mean pH stays the exact same. Like it might be adjusted a little bit. We want to see how good our buffer responded to pH and how well it neutralized anything that was added. Here we're adding 0.02 moles of NaOH. Okay, so it tells us that. It says, what is the pH of 1 liter, that's our volume of the buffer, of the, look, we have the same components from the previous problem. You will always have the same buffer. I will not mix up the components on you, okay? So if I tell you on the first part that you have this much of the weak acid and this much of the conjugate base, and here's the identity of your weak acid and conjugate base, that will be the same through every part, okay? You can count on that. I'm not going to change up those components on you. So we see we have the same buffer components, same concentrations. What happens though, how is this affected when we add some NaOH? Remember we said that the weak acid neutralizes strong base. It's the weak acid, acids neutralize bases. That's what we wrote earlier when we drew the buffer diagram. So the concentration of our weak acid is going to go down a little bit. It's going to get used up, neutralizing the base that we add. So here's what you got to do. Step one is you need to make what's called an ice chart. I'm going to explain this as we go, an ice chart. Okay. And what we're going to do on an ice chart is we're going to plug in our initial, I stands for initial concentrations of our weak acid and our conjugate base, whoops, which is F minus here, or I guess it's the NaF. So what are our initial concentrations? It's 0.1 molar and it's 0.12 molar. Okay, so we're just plugging in our initial concentrations. C, the C part in I stands for how is this going to change? We said the concentration of HF will get used up a little bit. So being used up means the concentration will go down a little bit because it's being used up to neutralize the base. So by how much is it going to go down? All right. And by how much is our conjugate base going to go up? And then we'll calculate those columns and we'll get our new equilibrium concentrations. And that's what we'll plug into the Henderson-Hasselbalch equation. Well, we got to calculate the change by looking at how much of our base we add. We're going to neutralize all of that base. Okay, so we need the concentration. Okay, concentration is molarity. So we just need to know moles of NaOH divided by liters. So we got to calculate the molarity of our NaOH. That's how much our concentrations of our buffer components will change by. All right, so what that equals is 0.02 moles NaOH divided by 1 liter, right? And our molarity would then be 0.02 molar. So we're adding this much base. That's the concentration of base we're adding to our buffer. So what's going to neutralize this base again? Is it HF or is it NaF? Which one? What do you guys think? Which one's going to be used up to neutralize this base? HF. Acids neutralize bases. So it's the weak acid here that's going to neutralize the base. So the concentration of HF is going to be decreased by 0.02 molar. It's going to neutralize all that base. So it's going to go down by that amount. So what's our new equilibrium concentration? 0.08. You just literally do 0.1 minus 0.02, okay? And calculate the total. If the concentration of HF is going down, concentration of the base is conjugate base is going up by the same amount, 0.02 molar. So the new concentration is 0.14. These concentrations are what you plug into the Henderson-Hasselbalch equation. And I have that right here for us. pH equals, what was our pK? We have that on the previous slide. Okay, we calculated pK. Same pK throughout every part of a buffer problem. 3.46 on this particular one, but it may not always be 3.46. Depends what your weak acid is. Plus the log of, okay, what goes on top, what goes on bottom. Remember, these are the new concentrations. We're not plugging in the original ones. They have now changed because they've neutralized the base we added. Yep, that's right. Conjugate base on top, so 0.14 divided by 0.08. What's our new pH?
Where did the 0.08 moles come from?
Say that again, Blake.
Where did the 0.08 molars come from?
We took the initial concentration, which was 0.1, and how much it changed by. Why is it changing? Because HF is the component that will neutralize this strong base. We're adding NaOH to our buffer. And HF is going to go into action and it's going to be used up. We're going to sacrifice some of that to neutralize the base. The base is threatening to lower pH. And HF has the ability to neutralize it by donating its acidic hydrogen ion to the OH minus and neutralizing it to make water. Okay, so if it's going to be used up, it's going to go down. The concentration will decrease by the amount of base that we're adding. So when we calculated the molarity, that's what we are plugging in right here on our change column. Does that make sense, Blake? So then we would do 0.1, the initial concentration minus the change, we get the new equilibrium concentration.
Okay, yeah, that makes sense. Thank you.
So our new pH is 3.7. So we see initially, what was our pH? Let me scroll, I'll come right back. Initially it was 3.54 before anything was added. And then when we add a little bit of strong base, the pH drops to 3.7. Or sorry, the pH raises to 3.7. Okay, so not bad. It kept it pretty close to what the original pH was. So that would be a good buffer. Okay, places where people mess up on this. They don't plug in molarity here. They would like look at the moles and plug that. And now I know the number of moles was equal to the molarity, but that won't always be the case. Like what I'm saying is the number of moles right here isn't always going to be equal to the same molarity that you calculate. You plug in the moles divided by the volume of your base. I'll always give you the volume. It may not always be 1 liter. It could be 500 milliliters or 800 milliliters or 2 liters. Okay. So step 1 here is always, number 1, calculate the molarity of your strong acid or base that's threatening to affect the pH of your buffer. Step number 2, once you get the molarity of that substance, set up your ice chart. Plug in your initial, plug in how they change, okay? Get the new equilibrium concentrations and you plug those. Step 3 is you take those new equilibrium concentrations and you plug them into your Henderson-Hasselbalch equation. Okay. I'm going to write we've got, oh gosh, 1 minute left. I don't have time. Here we're looking at how buffer changes, the pH changes when you add an acid. It's the same 3 steps. I'm just going to write the steps out because y'all are going to have to go in like 1 minute. We're going to, 1, calculate molarity of the acid, HNO3. All right, I give you the moles and I give you liters. Step 2 is you set up the ice chart. Okay. Step 3 is you plug in from the E column, E concentrations. To your pH equation, which is the Henderson-Hasselbalch equation, and you solve for pH, right? I will finish working this problem Monday in the review, or I might post a little supplemental video if I get time to. But you're going to work it the exact same way you did up here. The only thing is your minus and your plus will be opposite when you're adding an acid, okay? Because the conjugate base is what's neutralizing your acid. Okay, but I'll finish working this on Monday, okay? We'll have 1 buffer problem. Gabby, this is our last lecture, but you do need to watch the functional group video that's on Blackboard, 20 minutes